could you ever imagine that both of these graphs are representing the application that did the same amount of work? Welcome to Recycle Everything, or at least as much as possible. My name is Rafal Foltyński, and I'm a senior developer in LMAX. Yes, this LMAX that's open source the disruptor, and yes, we are hiring. I'm also an open source contributor and founder of appenders.org. So why am I here? I'm here to talk to you about the memory allocation and the GC pressure that comes out of it, and we're gonna make a step. I'm gonna show you how I optimized the software that I've developed, and made a step towards mythical zero allocation. So how are we going to do this? So I'm going to show you how I added some object pools where feasible. The library I'm talking about will use JSON. It will send JSON over HTTP. So I'm going to show you how I optimize that. Also, at some point, I'm going to show you how I took advantage of some of the architectural quirks in this library, and probably we're going to take a deep dive into some third-party libraries where I'm going to show you some tricks, how I found some of the improvements that could be made, and yeah, hopefully you're going to enjoy it. So I'm going to talk to you about some object pooling basics for a start. Then we're going to do some comparison of pooled and non-pooled runs, and then we're going to see how the garbage collection looks like in all of these runs. So if you're not familiar with memory allocation, the real life non-pooled example would be a birthday party where you have lots of guests, and every guest grabs a drink in a plastic cup, and once he finishes the drink, he just puts the empty cup anywhere, probably on the table, hopefully on the table or in a trash can, and then he grabs another drink. What we end up with is a lot of cups. So the idea of object pooling is to replace it with a limited set of objects that the guest could reuse, like glasses. So why do we use object pools? Usually you define an object pool where you would like to create some object that is expensive to create, and it takes a while. It's just expensive to create it at runtime. But it can also be used for a short-lived objects where the memory churn that comes from allocating a very large amount of these objects is so huge that it's just feasible to replace it with an object pool. There are a few recycling patterns. One of the pattern is borrowing, where you physically remove the objects from the pool, and then the new owner of the borrowed object has to explicitly return it to the pool. The other one is the reference counting, where you don't necessarily remove the object from the pool, but the pool itself keeps track of the reference count, how many borrowers actually borrowed a particular object. And the object can be borrowed, of course, once the reference count is 0. Once the object is borrowed, the reference count goes to 1. Also, some of the pools can be resizable, and the allocation when the pool doesn't have any elements, there are multiple allocation triggers that can be used to trigger creation of new objects. On empty, obviously, when the pool is empty, we need to add more objects. This is the simplest version of object pools. Another one is the load factor. This is the preemptive creation of objects. You try to figure out how many objects do I have in the pool, what's the maximum size of it, and if the pool is almost exhausted, you can allocate some amount of new objects to borrow. Also, the more advanced version is on lease return rate. You analyze what's the actual usage of your pool at the moment, and you adjust to it, allocate or deallocate where feasible, depending on how many objects were borrowed and returned within a certain period of time. Now, when it comes to resize strategies, you can resize linearly by a fraction of the initial size. For instance, if you have 100 elements and you would like to resize by 50%, your pool is going to have 150, then 100, then 200, 250, 50 objects. It can be a fraction of the current size, which is dangerous because at some point your heap can explode. Having 100 objects in a pool, resizing by 50% would lead to 150, 200, 225, and more objects exponentially. Also, you can decide to not resize at all, where at the point where there are no objects in the pool forces the user, the potential borrower, to wait until another object is available. This approach is common when you have a large when you have some memory restrictions, or you just would like to not create more objects than you specified initially. So why is it important in a scope? The takeaway number one from this talk I would like you to remember is that object pooling can be used to replace some of the pain points in our Java applications. One of the most common objects is one of the common mistakes that we do during development is serializing our objects to a JSON string. Don't do this. If there is one thing that you're going to take away from that, don't try. At least try not to allocate strings. Sometimes it's some of the have not optimized for strings. On top of that, strings, since strings are immutable, you're going to allocate a lot of memory once your traffic goes up. So have you ever tried writing the value to the output stream? I would like you to remember this line, because we're going to refer to that in the future. Now, why should I care about the memory allocation? Well, if we write our code in a way that it allocates a lot, it eventually leads to a situation where the GC overhead is so high that GC spends much more time collecting garbage instead of doing work. And we would really love our application to do work and not garbage collection. So the common mistake that we make is just increasing the heap size, just kicking the can down the road, and not actually fixing the underlying issues. And most of these issues can be solved by simply simplifying the code, tracking your allocation, and making the code better, or introducing some object pooling. So I've developed a library called log4j2 Elasticsearch, which is a log4j2 appender that is capable of pushing logs in batches to Elasticsearch directly from your application. And once you log a line in the logger, it eventually gets serialized. Log your message via log4j logger. It eventually gets serialized into a JSON, and then it gets appended to a bigger batch of objects, because Elasticsearch doesn't really like indexing a lot of single documents. Once you send these documents in bulks, it's very efficient to process it. The problem is that you can actually generate a lot of logs per second. The example that I'm going to analyze is sending 10,000 logs per second, and we're gonna compare different approaches to do that. The approach where both the first both the initial log event is serialized to a JSON string, and the resulting bulk containing 10,000 JSONs like these, plus um, plus the metadata for Elasticsearch, eventually creating a humongous string on your heap. So basically, if you're familiar with Logstash, instead of writing the application to disks, picking them up with Logstash and sending them to Elasticsearch, we're gonna send them from your application directly. And this is a fairly good case for optimizing file allocation, because you would really not want to introduce any libraries that would generate a lot of garbage in your application. So this approach, so optimizing file allocation first is a feasible approach. So going to the architecture of this library, once the log hits the appender, it's the serializer performs an allocation via after the log is serialized to string. Then the serialized log gets added to the batch delivery once enough logs are there, or once, for instance, if you'd like to send batches of 1,000 logs, the listener going to get notified, and then the next allocation, this huge allocation is going to happen when you create your requests to ES. So potential issues with that: the high memory allocation rate is obvious, but then the stop the world intervals start to kick in, and this is the moment where in profilers you're going to notice that your application is constantly doing some GC activity. Your CPU usage goes higher, and if you're spending your CPU on garbage allocation, you're not doing business. So I've created a series of tests. The baseline test that I've used to present this case is a test where I'm going to send 1 million logs at the rate of 10,000 logs per second. The message that I'm going to use, the log message, we're going to use exactly the same string, just allocate this particular string once. This string will be created from a 300 byte array, and this way we're going to be able to measure what's the actual framework overhead, what's the actual library overhead, how much memory JVM has to allocate using the underlying code to send these batches. And in order to see what was actually allocated on your heap throughout the whole run, it would be great to perform no GC at all. And fortunately, since Java 11, there is a garbage collector called Epsilon, which performs no GC, no garbage collection at all. The perfect use case for this is the application that just doesn't allocate anything. And if it does allocate, it has to fail eventually, because once you hit your heap limit, the JVM should just crash. So epsilon can be used in zero allocation services to indicate, for hopefully within your somewhere in your dev test cycle, one of the dev environments, that there is an allocation, application crashes. Please fix it, dear dev. So I've tried to push 1 million logs with a with one of the modules that I've developed called Log4j to Elasticsearch Jest. Under the hood, it uses a third-party library, including HTTP client, called Jest, obviously. And it turned out that in order to send 1 million logs, 1 million log messages, where every message has roughly 300 characters, it takes 20 gigabytes of memory on your heap to actually do that. So I started to dig deeper, and most of these objects, most of this allocation comes from bytes and strings and string builders. 14.5 gigabytes for byte arrays. That's quite a lot, given that the string that you're sending is always exactly the same string. And also over 70 million objects that are created somewhere on the serialization stack. The serializer used in Jest was JSON. I couldn't change it, couldn't replace it. Jest just uses JSON, period, and there's nothing you can do about it, right? Or is it? So let's see how the actual garbage collection look like. Let's try G1, because everyone likes G1, right? I've set the new size percent to 75 just to have both pooled and non-pooled runs behave more or less the same way. And non-pooled delivery took roughly 10 garbage collections to actually achieve the goal. Also, the CPU load was quite flaky. You can see two lines at the bottom. The green line is the process load. The blue one is the system load, and sometimes it spikes when you do some Firefox browsing, or you're doing any sort of background activity. For most of my tests, I try to just leave the laptop on the table, do something else. But unfortunately, some noisy Windows neighbors kicked in and actually affected even the process load. So in this case, you can see you should also see the 3.9% CPU usage, and you can use it as a point of reference of to see what's the overall usage across the whole run. This whole delivery took roughly 1 minute and 45 seconds. It's 10,000 logs per second. So 100 seconds equals 1 million logs. And when I started to dig, where is this garbage coming from, it turned out that a lot of classes are pre-allocating a lot of maps, which are then passed to another maps. And then we are using JSON to serialize it. We are using maps everywhere. We are using maps of strings, which is not necessarily the best way to serialize. Yes, JSON maps and strings everywhere. Definitely something can be done about it, right? So let's replace some garbage classes and add some object pools and see what sort of results we're gonna get. So I thought about writing value directly to an output stream, but then the output stream would probably have to be a byte array. So I would have to allocate this byte array somehow, and end up in more or less the same place where I was before, allocating a lot of bytes instead of raw strings. So I thought about writing my own buffers and my own object pools. Fortunately, during one of the meetups, some ex LMAXians and other bunch of low latency guys told me, dude, just use Netty. I thought, oh yeah, maybe that makes sense. Let's have a look at Netty. But I want to write my own pool. I want to have some fun. Creating stuff is fun, right? So I had a look at Netty, and it turned out that I would probably spend years developing a reliable resizable buffers. But Netty had it out of the box. It was called Composite Byte Buff, where you can specify the initial capacity, and once you write into this buffer, it will just allocate. It will just allocate more if it needs to. Then the byte buffer can be wrapped in byte buff output stream, passed to the object writer. Job done. Sounds good. So maybe I could pull the byte buffers. So I compared the efforts and evaluated options, and I figured out that it's probably better to use Netty, but still write my own pool. The management of expectations would be very difficult, and complexity might be extremely high. Uh, dealing with all the cases, big Indians, little Indians, dealing with chopping, slicing byte arrays. I'll let Netty do that and write my own pool regardless. So I've designed an API called I call it item source. I don't know why. That sounds like any other class, which can which will allow me to actually pull any type of object. And in my case, I can just create a item source pool of byte buffers. I can say, give me a pooled item source, and then once I do my stuff, I can invoke the release on the item source object, where via callback the object would add itself back to the pool. Uh, the pool expands and shrinks automatically. It expands on empty, simplest approach. It's quite configurable, and I'm already using this pool for three types of objects in this library. This way, I can write code like this, and eventually end up with a full implementation of the serialization. Given the object writer, uh, I can borrow the buffer from my item source pool, create the byte buff output stream called reusable. I'm not sure why I called it reusable, but it was just a heat of the moment, I guess. And eventually um, write the log event into the output stream, and then release it once it's ready to release. So given the non-pooled delivery architecture that you saw before, I've added a few item source pools for different types of objects. The first one on the left will be a pool of tiny buffers around 1 kilobyte, but it is meant to store a single log item. The pool on the right is the pool in the middle is the pool for the big payloads for HTTP entities. This will be a pool, a very very small pool of big buffers from megabytes up to whatever megabytes you wish to. And the item source pool on the right inside HTTP client is the pool that is used for uh, pooling the responses, because it turns out that Apache HTTP client allocates a new pool of a new array of bytes every time it gets a response. When I'm sending 10,000 logs, responses from Elasticsearch are quite high, are quite large. So there's no points in allocating a new byte array every time. We can just reuse the old one. Now the threads will be quite important here, because um, once you start to introduce object pools, it would be ideal to do the whole work within a scope of a single class. But unfortunately, not always the case, and sometimes you will have to release your buffer within the scope of other threads. In this example, you have application threads that would like to log something, serialized logs. Um, Logs serialized to borrowed buffers will eventually land in some sort of in-memory store. Then the notifier thread will pick it up, borrow another buffer, and it's the HTTP client that will release all of these buffers back to the pool once the response is ready. So this leads us to takeaway number 2: know your threads, because this approach may lead to issues that you didn't expect. And once you know what your thread is doing, you will be able to identify what sort of code you would like to write to actually handle object pooling properly, and don't create any memory leaks. So I've tested the pooled delivery with Jest and G1 as previously. It turns out that the CPU usage dropped by 50%, and also the memory allocation was much lower, and there was only a single garbage collection on the right once G1 learned. A few garbage collections on the left is the learning phase. So after a while, G1 learned that it's okay to let the application allocate a bit and collect the garbage not as often as it used to. So this is the same run with Epsilon. Eventually, it allocated roughly 3 gigabytes of memory. If you remember, in the previous run, the amount was 20 gigabytes. So by simply rewriting some objects and getting rid of some bad code string allocations, I managed to reduce the over 6 times. And also, the total number of created objects dropped from 240 millions to 42 millions, which was still a lot. And the actual amount of bytes get dropped from 13 gigabytes to 1.4, which is much better. But some Google code was still annoying. These were the actual maps created by the index requests. But eventually, I started to see 1 million buffered index classes that I've created to replace the default Jest implementations, and they started to be visible on the first screen of this whole memory tree, which was an improvement. So the immediate impact was that the interval between stop the world pauses drastically increased, and memory allocation got reduced a lot. The negative impact was the increased complexity of the code, and this is the thing that we as a have to worry about a lot, because the more complex the code is, the less maintainable it is. And also, once you start to do that, there is a very very high potential to create memory leaks if you don't if you don't if you don't handle literally every possible case where an exception can be thrown and the pool and the buffer is not released. So, takeaway number 2: know your threats. This is quite important while you do that. But can it get better? Of course it can. There are very very rare cases where something cannot be improved. So, what can we do about it? Let's write a completely new client from scratch, because I ran out of options with Jest. So I've decided to just take the Apache HTTP client as Jest did, and just write a completely new API and new API on top of that. The API that is focused solely on lowering the overheads and decreasing the memory allocation first. So, interesting, Log4j2 Elasticsearch HC, which was released at the beginning of this year. HC because HTTP components, obviously. And the first run with Epsilon was just blowing my mind. I finally managed to deliver 1 million logs with less than 2 gigabytes of heap. And also the CPU usage was very low. There is a very small amount of noise over that, and I can finally see most of the objects that I've created during the delivery. Delivering 1 million logs, you can see a lot of positions here, a lot of objects created with amounts exactly 1 million objects, and some of them are have a bit higher number. This is the architecture thing and the implementation details. For instance, concurrent link queue is not go for array lists or any type of list. Let's go for a queue, because why not? It turns out that concurrent link queue creates a node every time you return the object to a pool. Every time you insert the every time you offer the object. Also, I said hello to Jackson objects, because I've decided to not use JSON, because Jackson looks much better here. However, it turned out that Jackson creates Jackson creates a UTF JSON generator and IO context and 2 JSON write contexts for each object that I'm creating, which was curious. And let's see if we can do something about it later. Also, I saw my reusable stream, and I thought, is it really reusable? Maybe it's time to actually make it reusable. Plus Log4j events. Why am I getting so many Log4j events? And well, I'm sending 1 million, obviously, but I've tried to set up Log4j to actually reuse all this stuff. So what is all that? And I was quite happy to reduce the amount of memory allocated from 20 gigabytes to 1.9 gigabyte per 1 million logs, since memory allocation is quite predictable. You can create a reference test that you can just use for any type of code and get very predictable results with that. So 24 millions objects instead of 240 millions, plus reducing the allocation from 20 gigs to 2 by mainly object pooling and removing some garbage classes from your code and optimizing some algorithms. Way to go. Now, can it get better? Of course it can. It can always get better. So let's introduce Elasticsearch HC with some crazy ideas that I haven't released yet, but some of them are very close to be commit ready. And I'm gonna walk you through some of the interesting places in code that I found, um, and how I managed to improve that, or rather hack it in to actually get the memory allocation as low as possible. So the next steps that I've took was just tracking the memory, every object that was created. I was trying to figure out where and why this object is created, within which thread. Can I control the lifecycle of this object? Can I call release or clear or whatever other API method on this object to actually get it back to the pool? And spike some improvements, and of course measure afterwards. So three elements that I wanted to focus on was the concurrent link queue, which I just replaced with JC Tools queues. If you haven't used the tools yet, try it. This is a proper set of collections that every JDK should have. Also, Jackson generators and IO context and JSON write context were consuming 250 megabytes per million logs, which was quite a lot. So the solution would be to just write a custom object writer. But can it be done? How hard is to actually reuse the same generator? We definitely cannot do that with in a non-thread safe environment. So yeah, some hacks or assumptions have to be done. Also, Log4j2 events were consuming over 200 megabytes per million. So let's just introduce the pool into a logger disruptor config, because why not? Unfortunately, the architecture of the design of the default async logger config disruptor does not allow any sensible extensions. So basically, what I had to do was just copy the whole class, and there was not a lot of stuff I could do with that. And I'm not even sure about releasing this piece because it's still quite unstable at very high rate of logs. Is just a bit unstable. Let's have a look at some pieces of the code. So the first thing that I wanted to replace was the UTF JSON generator, and UTF JSON generator was created via multiple different constructors. But what I did want to focus on was the IO context object and eventually output stream. So output stream is final, which means that I probably shouldn't change that. I could create a PR and ask the creator, is it feasible to actually reassign this output stream? Final fields in classes are there to remain final, and I'm not a fan of making the class immutable just so that some developer somewhere in London wants to have some fun. The other object was the IO context. This goes eventually to the superclass and also gets assigned to a final field. So theoretically there was not a lot I could do about it unless I create my own versions of output stream and IO context that I could actually change. So the extended UTF-JSON generator will actually not close the generator properly. Also, it will not release the buffers, the underlying buffers, and since I can control the creation of this generator, I can just put an output stream delegate, a class called that I called output stream delegate, which allows me to replace the output stream whenever I feel like. Also, replace some fields inside the IO context, which would allow me to reuse the same object that I've created at the beginning, but for another log event. And also, JSON write context can be reset. So why not just do that and reset it? And on every new log that I'm creating, when the actual underscore create UTF generator method is called, this is the method from Jackson call stack. I'm just delegating to single thread UTF JSON generator. If it was already assigned, let's just reset it with new output stream. I hope that makes sense. And if you look around, your code and the third-party libraries, you will probably find a lot of these spots where this sort of things can happen. Unfortunately, since the object writer and object mapper should not be accessed by multiple, or rather these versions of generator and IO context should not be accessed with multiple threads. These classes are not thread safe. If you try to access and if you try to serialize your objects in multiple threads, they're just gonna break. But fortunately, this is the place where we can make an assumption during the configuration. If the user knows what he's doing, he can just decide to declare this item source factory as a single threaded one, and log in when configured to use async loggers will deliver every log event within the scope of a single thread. So takeaway number 3, know your call stack. You have to know exactly what is going on your in your libraries. Know your threads, know your call stack, and this way you'll be able to leverage some protected and package private bits from the third-party libraries that creators may not necessarily intended to allow to use like that. But hey, it's open source. So back to the architecture. The application thread on the left can actually be replaced by disruptor consumer thread. This is the thread that takes items from the disruptor and delivers them to Appender one by one. So I can leverage that. Use the single threaded JSON generator, and hopefully not break anything. I'll probably release this codes in a few weeks. I just need to run some more performance and stability testing to actually prove that it works as I expect. Also, I've replaced the disruptor config. Instead of creating logs, creating new log events every time the new log arrives, I'm just taking the pullable log event from the pool, and this way I managed to get rid of at least the set of objects that I mentioned before. Fortunately, along the way, a bit more objects got cleaned up, because it turns out that some string array sorted maps are not created anymore, or I'm getting it much less accidentally created hash maps, which were part of the Log4j implementation. But for this particular case, I don't need all of that. So let's see how it runs. So delivery with the development version of the HC components needed 6.2 millions of objects to actually do the same amount of work as the previous previous two, the Jest one and the current master. Also, a total of 549 megs was allocated to deliver exactly the same, to handle exactly the same workload as the previous string-based non-pooled Jest did. Finally, I can see the classes that I'm using. This is a part of part of the API that I decided to not pull yet. First of all, it was quite tough to do that because of some architectural mistakes that I did. But in this case, it actually shows me that it does the job it says it initially meant to do. Also, the allocation of bytes got optimized a lot. 13 and a half gigabytes initially, which then dropped to 1.4. Now it's only 330 megs, where most of these bytes are just buffers, which eventually led to a graph like this, where the CPU usage was super low, barely noticeable, you could say. If anyone asked me, would you imagine that this application is delivering 10,000 logs at the moment? I would say, no way. 10,000 per second, 1 million. So the memory allocation graph is almost flat. Most of the allocation at the beginning are just buffer allocations, and then during the actual runtime, there is not a lot of allocation happening. So if I would like to test the actual garbage collection, I would probably get old, grow a beard, plant a tree, and still not get enough data. So let's increase the load to actually get some data about the garbage collection. Let's establish new baseline, and of course measure again. So let's deliver 100 million logs. Same rule applies. Single string, just to indicate what's the framework overhead. This time delivering 50,000 logs per second, because why not? It turns out that Elasticsearch cannot handle it, and so I had to write my own fork that just doesn't store these logs, because that was kicking the system through the roof. But it responds as it's written these logs properly, just to put some pressure on the deserializers and verify that everything works as expected, as it would with a real Elasticsearch. So I also decided to switch to ZGC, Java 14, in Java 14, ZGC was finally released to Windows. So why not test it out? There were less than 70 proactive collections. This will be important in a minute. I can finally see the CPU. CPU usage was roughly 5%. I'm getting some stuff in the chat. Not too long, Ben. I should probably finish in around 5 minutes. Sorry for that. I could finally see that the CPU usage was quite stable at roughly 5%. So let's see how Jest is doing at 50,000 logs per sec. So the initial graph that you saw, allocating 20 gigs in this version, it got sped up a lot and doing 100 times more work overall than it used to do. There were over 1,600 collections caused by the allocation rates. This is important with ZGC. The proactive and allocation rate are indicated as causes of the GC. Also, the CPU usage was much higher, so this clearly indicated that that object pooling helped a lot in this case. And 13% versus 5%. When you extrapolate it to hundreds of servers doing some work, you can save thousands or tens of thousands of dollars, maybe even more on your infrastructure. Thanks to this approach. So let's have a look how the GC events looked like. I used GC Easy to actually show what was going on, to analyze the GC logs and figure out what was going on inside. But the GC events graph was not helpful, since there were like 1,600 of them. So this is a distilled graph of 1 minute of GC events during this delivery. To compare, this is the whole run with ZGC and the development version across half an hour, and this was the garbage collection during this minute, more or less. So in the end, I have reduced the pulse time from over 3 seconds to just 147 milliseconds, where average time didn't change much, but the concurrence time spent, the difference was vast. And also, this pulse time spent in Jest, the average times are the same. It's just the rate of GC that is much lower that causes this difference to be so big. And this is the comparison of the current HC module in master, latest release, 1.5 seconds roughly. The average time spent on GC was a bit higher. I don't know why. I need to track it down. But overall, a lot of stuff checks out. The memory allocation comparison looks just insane. Jest needed almost 2 terabytes to deliver 100 million logs, where the crazy development version needed only 13 gigabytes. The allocation average creation rate almost a gigabyte versus 6.3. I think it's a decent improvement. The current master allocates roughly 94 with the same workload. Also, the GC throughputs got much better. The GC throughput indicates how much time is spent to do the actual business work. The higher GC throughputs, the more work your application is actually doing outside of GC, which means that Jest was spending a lot of time over there. The crazy HC dev version needed only seven thousandths of percent to actually do the GC work. So I reduced the pause time from roughly 7 seconds per hour to 0.3 seconds per hour. And the question that you might have is, was it worth it? I would say absolutely. First of all, it's a decent improvement. On top of that, you're going to get to know your application stack and threading and what your threads are doing much better. And it was also there was also a lot of fun while doing that. I had a blast. That's all I have for today. Do you have any questions?